Welcome to this video on numerically solving unconstrained optimization problems. In this video we will talk about how you can code up algorithms for solving such problems yourself and how you can use scipy.optimize to do it for you. The scipy.optimize way is always the safest and the fastest way to do it, but it's also good to understand a bit about what happens underneath. If you want to understand even more of that, I could recommend this note by Anders Munk Nielsen. I will import the standard NumPy and plotting stuff, and then I will use linalg and optimize from scipy. Just sort of to get us started, all optimization problems can be characterized sort of in three things. First, there is something we control, a control vector, choices, decisions in an economic problem. That's some vector of real numbers. And then there is an objective, a payoff, a utility that we want to minimize. That's a function f that goes from this choice into the real numbers. And that can be differential or it can be not differentiable. And finally, there could be constraints that we are in some way required to choose from a specific set. We will not cover that today. In general, our function might also take other parameters or data set or whatever, but since we don't optimize over these, since they are fixed, we don't care about them. I said we wanted to minimize just before, but if we want to think about maximization, then it's just a minus in front of our function. Then we are minimizing the negative version of the function. That's the same as maximizing the function itself. All optimizers sort of have the structure that you first make some initial guess, then the optimizer will evaluate the function, and perhaps it will evaluate some gradients of the function. Then it will check whether we have converged, and if not, it will update the guess in some way and return back to step 2 and evaluate the function again and continue until convergence has been hit. And by convergence is simply meant a small change in the function value since last iteration, or a zero gradient, that it seems like the function is flat here, so you cannot improve anyhow. So that's always sort of a local statement about the function, that it doesn't seem to change anymore. In general, sort of gradients can be useful for this because they tell you about how the function slopes, so you know something about in which direction you move to get to the minimum, but they can be costly to compute, either using an analytical formula or even if you have to do it numerically. So that's always a trade-off of whether you want to use these or not. There's many optimizers out there. I think 3 optimizers that is useful to know, and which I will talk about in this video, is the Nelder-Mead optimizer. The good thing about that optimizer is it is very robust. If you have a objective function that is not very smooth and does not have nice derivatives, then that's the way to go. The problem is that it can be slow. It takes many steps to converge. On the other hand, there is the Newton CG method, which generally require very few iterations, and if you have sort of an analytical expression of the Hessian for smooth functions, it can be very precise. On the other hand, it's costly because you need to compute the Hessian, and that's not always that nice. A good third option is therefore BFGS, which is like Newton, but with a smarter computation of the Hessian based on the gradients. That's generally require fewer iterations, and sort of the only thing speaking against this is that it's slightly less smooth in terms of convergence. But you'll also see that later on. It's always a good idea sort of to try each of these out if you have a problem at hand. But first, let us talk about gradient-based optimizers. So the idea behind gradient-based optimizers can be sort of shown in a one-dimensional example. So if you consider a second-order Taylor approximation around some xk, then sort of the Taylor approximation will say that that can be written for any x as the xk plus some change in x, and that will approximately be the function value at x times the derivative of x plus the change in x plus half the second derivative of the change in x squared. And now the idea is that if we use this second order Taylor approximation, then we can find the minimum with respect to the change in x by solving the first order condition. So taking the derivative of this with respect to delta x and solving this, we get out an expression for the change in x, which is minus the first derivative over the second derivative. So this is sort of saying that if this Taylor approximation is correct, then this is sort of the step size we should take to go to the minimum of the function. So that being sort of used to say that if we are somewhere, then we know this is probably a good step to take. So that gives rise to this minimize Newton algorithms, which is sort of say that we should start choosing a tolerance. We should start guessing on some value of x, then we should compute the function value, and we should set a counter equal to 1. Then we should compute the gradient, the Jacobian, and we should compute the Hessian. And then we should compute a new guess by saying that our new guess should be, and this is a small mistake, there should be a k in there, that the new guess should be the old, and then minus, and then we take basically the second derivative, that's now the Hessian, and divide it into the first derivative, namely the Jacobian. And now we evaluate our function again, and we can see whether we have convergence. Then we stop, otherwise we increment our counter, and we compute the gradient and the Hessian, and we continue doing this. Okay, so let's see how we can implement that in practice. So if the minimize Newton function here, that takes the function as a callable, it takes our initial value, and it takes callables for how to compute the Jacobian and compute the Hessians. Then there is a maximum number of iterations, and there is a tolerance. And finally, there's sort of a use solve option, which can sort of do something else in this updating step. I will tell you about that in a second. It always returns sort of the x, that's the minimum, and the number of iterations used. So we initialize by setting our x equal to our initial guess. We set our function value even to the function value there, and we set our number of iterations equal to 1. And then we say, okay, now we want to continue updating for at most the maximum number of iterations. Each time we sort of remember what was our x and our function value at the last step, and then we evaluate our Jacobian and our Hessian in these. And then in our update step, we simply apply the formula above. One bad thing about that is we need to compute the Hessian. So we can also instead sort of think about this as a solution to an equation system that can numerically be a bit more stable, but it gives exactly the same results in the examples that we will look at. Then we will calculate the function value at the new x and see whether we have converged. If we converge, we break out of our loop and we're done. Otherwise, we increment the counter and we go back and continue doing this. Okay, so this is an important function to understand. So this is a good time to pause the video and look how does the algorithm compare with the code. Does this make sense for you? Okay, I hope you have done that. Otherwise, let's look at an example. So here is what's called the rosenbrock function. That's just some function which looks like this and have the following Jacobian and Hessian. If you look at this function, you can sort of see that we know that the global minimum must be at 1,1 because then this function is 0 and it will be positive otherwise because we are squaring these terms here. So we know that we want to find 1,1 and that's where the function is 0. I forgot to run this, so now it's in memory. And then I define the Rosen function. And we can sort of have a look at it here. This is just plotting code. We sort of give us our 3D picture of how the function looks like, and we know that sort of it's in 1,1 up here somewhere that the minimum is. We can sort of also do a contour plot of it, where we can sort of see that the minimum is here in 1,1, and sort of this is sort of lines where we have a constant function value. So this is sort of a function that's often used for testing optimizers. So let's test our optimizer on it. I choose an initial guess of 5,5, and I just run this. And we can see that it ends up after 6 iterations in 1,1, and the result is 0 as it should be. Also, if we set use solve equal true, we get the exact same result. Okay, so our algorithm actually worked. Okay, so one thing that was a bit irritating here is that we needed to compute this this Hessian up here, and that's either we have to do that analytically or we have to come up with a numerical approximation of it. So another kind of algorithm which use gradients still, but it's a bit simpler, is something called gradient descent. And the idea here is that we again start by choosing a tolerance, and then we choose some potential step sizes, a vector of alphas, which is just some numbers. Then we guess on an initial value, and we compute our function at this value, and then we set our counter equal to 1. Then we compute our gradient, and we then we find a good step size. So we search over all our alphas, and we find each time we evaluate our function in our previous x minus alpha times the gradient. So we sort of, if the gradient is positive, then we will sort of say we need to have a lower x, so we will step towards a lower x, and the higher alpha is, the more we will step in that direction. And then we simply try out all the alphas, and we see which function value is the smallest, and then we sort of say that's our function, that's our step now, and we compute our new step using this alpha star that we got up here. The conversions is the same if we have that the absolute value of the difference is smaller than in our tolerance, then we stop, otherwise we increment the counter and go back. The minimized gradient descent algorithm again takes sort of similar inputs, the function, the initial value, and the Jacobian, and then these alphas and the maximum number of iterations and the tolerance. Note there's no Hessian needed here. The function returns the x value and the number of iterations and the number of times we evaluate the functions and the number of times we evaluate the Jacobian. So we initialize things exactly as before, and we set our number of iterations and number of function evaluations. And then we, very similar to before, note what was in the previous step, what is the Jacobian at this point. We update the number of evaluations of Jacobian, and then we start out by saying, okay, what is the best function value we can get at? We don't know that, we say that that's infinite. And what is the best x and the best alpha? We don't know that, so we put that as not a number. And then we go through all our alphas, and each time we update our x, we try to evaluate it, so we increment the counter of function evaluations. And if our function value is lower than the best function value we have seen yet, then we update our information on all the best things we have seen. So this sort of makes a number of function evaluations, and when that's done, then we know that our x will be the optimum from this small loop up here. And we know that our function value will be the best function value we have seen, and we can check whether this is close enough for convergence, or we need to update our counter and continue. Okay, so let's put this into memory and let's see whether this works. We can see that we sort of converge. It's not sort of the most precise 1-1 we could get at, and it takes a lot of iterations, but it is sort of an okay approximation of 0. Yeah, it's a good idea again. Spend some time looking at the code, looking at the algorithm, and see how it fits together, and see whether you understand everything. And if you want to, you can perhaps also try to play around with the alphas and see whether you, by changing these alphas, can sort of get faster convergence or get more precise convergence or something like that. These alphas was something I just sort of tried out, and that seemed to work okay. But you can perhaps come up with something better. If you find something really good, please throw me an email with it. Okay, so this was 2 examples of how you can implement optimizers yourself. Now let's also look at some stuff that can be done with SciPy. So we want to understand a bit about how the SciPy minimizers are working. For that, I will define 2 functions, a collect function and a contour function, which is not that important that you understand. They're just there for plotting. So let's just evaluate these and let's forget about them. And then I want to show you the nil-meet algorithm first. And what I do is I set the number of iterations equal to 0. I use that in the collect function above. Then I choose some initial guess. And then from optimize, I call minimize on the rosen function with my initial guess. I choose the nil-meet optimizer. I use my collect function as a callback. That means that it's called before each iteration. And that way I can follow what's going on. And I wanted to display the results afterwards. And finally, I call my contour function to show how the optimization has progressed. So let's run this, and you can see that it gets to a function value at 0 in 57 iterations, and it needs 105 function evaluations for this. And sort of in the contour plot here, you can sort of see this is where we start out. We start out in minus 1/2, minus 1. And then you can see how the optimizer moves. It seems to improve the function value always, but it makes up some weird detours here. But it ends up in 1/1, so that's good. If you sort of look at what happens to the function value at the number of iterations, you can sort of see that it starts with a very high value out here, and then it always goes down. But it actually reaches something that's very close to 0 even after what, 18, 20 iterations. But then it takes a lot of time to get to the sort of the fine tolerance that we want. So this is sort of a property of nil-meet, that it can be hard to get the last step of the way, to say so. Okay, so that's a case, and that's the problem with the nil-meet. But in other dimensions, it's very robust. Okay, you might notice that the number of function evaluations is larger than the number of iterations, because it uses sort of some extra function evaluations to have some idea of where it should go. So it's not a gradient per se, but it's sort of something that's a bit more, that's a bit similar, but a bit more robust. Okay. Once we have computed these results, we can also sort of look more into them. So notice that the optimize minimize returns this result thing, and we can look into what that is. And that tells you something, the final simplex, that actually where it's searching in the end. It's tells you what the exact function value is. It tells you something about whether it was successful, and this number of iterations, and whether it was a success, and it tells you the x that come out of it. And we can sort of get specific information from this object, for example, the number of iterations. Okay. Another optimizer you could use is the Newton optimizer. So let's see what that does. You can see it needs very few iterations, and you can see that it just beautifully zeroes in on the 1/1. So in that way, that is very efficient here. But it also requires us to specify both the Jacobian and the Hessian. So that's sort of that's the downside. And this will only look this beautiful if the function itself is smooth enough. You can also say that you only know the Jacobian, and therefore you will want to use a Hessian instead. And you want it to compute the Hessian instead numerically. And you can see that this still works well. It's sort of the same number of iterations, but instead of Hessian evaluations, it's now using more gradient evaluations to sort of get an approximation of the Hessian. So that's nice. The third alternative that it's good to know is the BFGS algorithm. That's always using the Jacobian, but never the Hessian. It's not quite as smooth as the Newton, but it requires very few function and gradient evaluations. So in that sense, it's very efficient. It has taken some weird step here, which is not clear to me why it does that. But it zeroes in, and it sort of, once it gets close to 0, it's good at sort of getting the final step of the way. Again, we can, instead of specifying the Jacobian, we can actually just let SciPy do that internally through a numerical approximation, and you can see that it works almost as well. but now I think it needs more function evaluations. So before we only needed 14 function evaluations and 14 gradient evaluations. Now it's needing some function evaluations when it does the gradient evaluations, basically. Yeah. So this is a general thing you can do. Okay. So now we just call these optimizers with the sort of the default settings, but there's a lot of settings you can change, and each optimizer has its own settings, and you can sort of look up in the documentation what that are. Two things that are good to know is that we can change the tolerance. So here for the BFGS, for example, there is the gradient tolerance, sort of how small should the gradient be before we stop the GTOL, and I try here two numbers, 10 to the power of -8 and 10 to the power of -10, and I set that into my options. So if I run this, you can see that it converges with our 10 to the power of -8, converges in 14 iterations, while if I lower the tolerance to 10 to the power of -10, then it takes one iteration more and get therefore a bit more precise results. Sometimes you might have a tolerance of that's very fine. Sometimes it's okay to sort of do it roughly, so you can sort of do it in that way. At other times, you might be at a very sort of constrained computational budget. So you simply want to say that there's only this number of iterations that I will need. So I will only use 5 iterations. So you can see here that now it stops somewhere that's far away from the actual minimum, but you have only done 5 iterations. So in that sense, that's what you told it to do. You can also see that while up here, it sort of stated that optimization was terminated successfully. Here, it's sort of warning you that the maximum number of iteration has been exceeded. So that is, it has not converged within this maximum number of iterations. So a task for you is try to pause the video here and try to make the program stop if the optimizer is not sure it has found a maximum. So try to do that. Okay, so what we could use is that we could use this result struct here. And if we have a look at that result, then you can see that there's something called success. And now this is false. So now if we say that we assert that result dot success. So now we require this to be a success. But here it gets an assertion error, and we could sort of plug in our function convergence not achieved. So now we sort of get this achieved, not successful. That I know I can spell. Yeah, I think something like that, right? So that's not that's how you basically do that. So that's always good if you want to be sure that you've actually found a minimum, then you should look out for these. And if you do many optimizations one program, then it's hard to look for them yourself. So it's good to sort of make the computer make you aware if it's a problem. Okay, now let's turn to a second example, the Griewank function. This is a function that has this weird looking expression here, but note that if you put in zeros everywhere, then all of this sum here is zeros, and if you take the cost here of zeros, then that's 1. So if you multiply them together, that's -1, and then we add a 1. So everything will be 0 if all inputs are 0. So we know that this is the minima of the function. But the thing is that this function also has many local minima. And the question is, how can we avoid this? So let's just create the function. Let's see what the function is at 0. It is 0, but let us also plot the function. And this is just some code for plotting it, and we're going to see, okay, it looks nice. It's it zeroes down on 0. That seems to be good. This is in our big range up here. But then if we zoom into a smaller range, we can see that the function becomes very complicated because now it's really it has a lot of local minima in all of these places here. So, and it doesn't really, it gets better if we move all the way in, but if we start somewhere out here, then it's not clear that we will converge to the actual global minima. We might converge to a lot of local minima. So the way to sort of alleviate that problem is to use multistart. And what I will do is that I will draw some initial random starting values, and then we will run an optimizer based on that many times. So here I'm just drawing my x0s, my initial guesses, from minus 600 to, and then this will be a random uniform number, so it will be from minus 600 to plus 600. And then I will just create some space for remembering which x's and function values I end up with. And just to check that the minimum and the maximum value that I'm using here is very close to minus 600 and plus 600. Then I say, what is the optimum function value I've seen? What's the optimum x I've seen? I don't know yet to begin with, but I loop through all my initial values. And for each of them, I start a BFGS optimizer, and I remember the x I end up with, and I see what my f is, and then I print the first 10 function values that comes out, or if it's the best function value yet. If it's the best function value yet, then I save it, and then I plot then I print at the end what the best solution was. So if I run this, then you can see that first I print what is the initial values that I start at. Those are just random, and then I print what I converged at, and they also look a bit random to be honest. And you also see that the function value is really not 0 here. So this means that it must have converged to some of these local minima that the contour plot up here shows. But we can see that eventually at my 2302nd guess, it's actually converged at a 0, and then it doesn't find anything that's better than that. So sort of I succeed, but if we sort of plot where all my optimizers converge, you can see that it converges all over the place. If you do a histogram of it, then you can basically see that it seems like it's almost uniform where it converges to. So that's a really bad function to optimize over, because it's so hard to get into that global minimum, and our optimizers will end up in a local minimum. And multistart is the way to go, but of course you never know how many multistarts you need. But you often do a certain number, and then you try to double it, and if it doesn't change the results, then you think that you have found the global optimum. But especially in high-dimensional problems, this is hard to know. But there really is no sort of better solution overall. One thing you can do that can do a potential improvement is you can use information from previous function evaluations to know where you should look next. And in that there's a fundamental trade-off between exploitation and exploration, where exploitation, you want to focus on the areas where previous function evaluations have returned low values, because that seems to be where the minimum are. On the other hand, there might be a completely different area that has a very low value, so we also want to explore somewhat and go over there, and that's a hard trade-off to do. But if the same optimum is obtained from many starting values, that's also a good sign that this is actually the global minimum. There's a link here to a research paper that sort of discuss how you can sort of use these global optimizers, where you do some kind of multistart to alleviate the local minima problems. But this is somewhat advanced stuff. Thank you for today.